Dear friends, today we'll be starting a new chapter on equilibrium. So, all the while studying the thermodynamics, we have understood that thermodynamics actually deals with equilibrium states. And we had also studied that equilibrium would typically involve mechanical equilibrium, chemical equilibrium, thermal equilibrium, etc. So basically, equilibrium is when the forces are balanced. So when you have a single object which is isolated from all other objects for interaction, from interacting with other objects, then within the object there should not be differences between generalized forces for different kinds of interactions, so that there is equilibrium, so there is no spontaneous change that is. Now this, we had said, should involve mechanical, thermal and chemical equilibrium. So in a simple compressible system, where if I divide the object into multiple segments, then between different segments of the object, there should be no difference in the various generalized forces that prompt the various interactions. For example, if the pressure is different between different parts of the system, then there can be mechanical work, there can be displacement work that can take place between those 2 points. If there is a temperature difference between 2 parts of the same system or same object, then there can be heat extracted from one part and heat rejected to the other part running a heat engine, so there can be net work output, and therefore there can be some spontaneous interaction. Or if there is a difference in composition, so if you have multi-component systems, and if I have difference in composition between 2 parts of an object, then there can be mass transfer, which can result in chemical work. And therefore, if I need a system to be in equilibrium or an object to be in equilibrium, then it needs to have uniform temperature, uniform pressure, and uniform composition in its volume. This is something that we have studied as part of the first chapter of the course. So in this module, when we discuss about equilibrium, we'll actually go through these things a little bit more formally and in detail, and derive what we call as the conditions for these equilibrium to exist. Or we'll start with simple substances and pure substances and derive the condition for this equilibrium, and then extend this condition for multi-component, multi-phase systems, so as to understand phase equilibrium. So this is basically what we will try to do. So when I say that we need to have equilibrium, what do I mean? Let's go to the whiteboard and start working on that. So let's say condition for equilibrium. So condition for equilibrium between objects is something that we derived as part of the first part of the course, where we said that the external force should balance the generalized force so as to have equilibrium. But when an object is isolated and left to itself without interacting with any other object, so suppose I have an object like this, and let's say notionally I take 2 partitions of this object. So let us say this part is part 1 and this is part 2. Suppose there is a temperature T1 and there's a temperature T2 here. Let's say the pressure is the same, P1 and P1. Then if there is a temperature difference between these 2 parts, then I can actually, let's say T1 is greater than T2, then I can extract heat from here, run a heat engine and produce net work output and reject the heat here. So there can be transfer of energy between one part of the object and another part of the object, and in the net you would be actually producing some work output. Now this is then a system which is not in equilibrium. So T1 has to be equal to T2 in order to have the system in equilibrium. Similarly, suppose I have an isolated system which is consisting of, let's say, a piston in between. Okay, so let's for a moment assume that this is also T1 and this is also T1, but there is a pressure P1 here and there's a pressure P2 here. Then this piston can move, and if I connect the piston to a rod that goes out of the system, there can be work output here. Right? So P1 has to be equal to P2 in order that there is no net work that is coming. So the system then stays at the given conditions. So temperature equality and pressure equality is something that we understand. So this is thermal equilibrium when T1 equals T2, and there is mechanical equilibrium when N1 when P1 equal to P2. Similarly, if I have an object which is notionally divided into two parts, and let's say here also you have Tp and here also you have Tp, the temperature and pressure are same, but I have different number of moles. So let us say I have two substances, one as let's say N1 moles of species 1 and N2 moles of species 2 here. Let's say N1 1 and N2 1, and here you have N1 2 and N2 2. So if N1 and N2 are different between so N1 is to N2, the mole fractions of N1 and N2 are different in these two parts, then there can be chemical work UIDNI which can happen between these two, and therefore there can be non-equilibrium. So what it also requires is that the composition has to be the same between these two parts. So that is what we call as chemical equilibrium, which basically requires N1 1 is equal to N1 N1 1 by N1 is equal to N1 2 by N2, and similarly N2 1 by N1 is equal to N2 2 by N2. And basically this N1 is N1 1 plus N2 1, and N2 is N1 2 plus N2. So I have a two component mixture here, N1 and species 1 and species 2, and in this part 1 I have N1 1 and N2 1 moles of N1 over species 1 and 2, and here I have N1 2 and N2 2 species moles of species 1 and 2. Then the mole fractions have to be equal. So you have N1 by N1 by N1 1 by N1 to be equal to N1 2 by N2, so that the mole fraction of N1 is the same on these two sides, and similarly mole fraction of 2 is also the same on the two sides. Then you have what is called the chemical equilibrium. So this is basically what we initially understood. Now, if I try to go a little bit more in detail, then suppose this is a simple compressible system. We'll come to the multi-component system a little bit later. So let's say it has a pure substance that is there in it. Then so if I have only one mode of displacement, so it's a simple compressible system here, then its first law will basically give me delta Q is equal to du plus p dv. If the work is happening reversibly with the pressure being the same, and there is a change in volume of the whole system. And second law basically tells me ds is equal to delta Q by T plus sigma. Then if I combine these two, saying that delta Q is equal to du plus P dV, then I can write this expression as T ds is equal to, I substitute for delta Q from here, which is du plus P. Okay, so let me write it for whole system, so it will be capital U. So this will be also capital U. U plus PTV plus T sigma. So if I write the expression for T sigma here, T sigma would actually be equal to T delta sigma. So T delta sigma would actually be equal to T ds minus U minus P dV. Okay. Now this quantity we know is always greater than or equal to 0, and so we can write this as greater than or equal to 0. So if I look at this expression, which is a combination of first and second laws for a small infinitesimal change in state of this object, which is a simple compressible system, then if I maintain the S and V to be the same, then the condition for this process to spontaneously happen would be that minus du is greater than or equal to 0, or du at constant S V has to be less than or equal to 0 for a spontaneous process to happen. So what am I saying? So if I have a simple compressible system, let's say a cylinder piston, I have a cylinder piston and this is insulated, there is no heat transfer. Then if there should be some change in U here, then that can only happen. So the du has to be only less than or equal to 0 when I maintain S and V to be constant. So suppose I lock this piston, there is no interaction, then the heat can only go out. So du has to spontaneously be less than or equal to 0 in this particular case. So this is basically the condition for spontaneous process to happen. So what does this expression basically say? It basically says that if I leave a system to go to equilibrium when I don't make it interact with any other object, then the object would actually go to a state where the energy decreases, which basically means that if I plot with respect to, let us say, any state variable here, the value of u, then suppose there is a possibility of u coming this way or u coming this way from this side, then the process would only happen in that direction until it reaches, let's just say, the value of minimum u. So the process with decreasing u is spontaneously feasible, but once the state reaches here, the process to go to either side would require an increase in u, which would not happen. So basically the object has gone to equilibrium here and it will not change any further once it has reached that state. So the condition for equilibrium of an isolated system, therefore, is minimum internal energy when S and V are maintained constant. So this is basically what the condition that we were coming to. So if I have an isolated object whose entropy and volume are maintained constant, then so suppose I have an object which contains some substance inside. Okay, so initially, let us say the temperature and the pressure inside were not necessarily uniform, but we have isolated this, so there is no heat transfer, so there is no S, and there's no change in volume, so there's no V, so there is no heat or work added, then the total U of this object would go to a minimum so that the system goes to equilibrium. So when the system goes to equilibrium within itself, you will have its internal energy minimum when S and V are maintained constant. Now, once we have done this, then we can again look at the same expression. P ds minus du minus P dV is greater than or equal to 0. Now, suppose I maintain U and V as constant, then the system would go to a state where S increases. Right? So, if U and V are constant, then S goes to a maximum. Okay? So, that is the point of equilibrium, where if I plot S as a function of any state variable, then the states which result in increase in entropy would be spontaneously favored, but once it reaches the position of S max, then the process would go to equilibrium, and either way it will not be able to move, because moving on this side or this side would violate the combined first and second law, and therefore would not be possible. So this point would be the state of equilibrium. So the state of equilibrium would be the state at which the entropy of the isolated system is a maximum. So this is the principle of entropy maximum that we typically state for an isolated system. So if I consider the object which is completely isolated from the surroundings with no interaction possible, then the state of equilibrium would be the state of its maximum entropy. Right? So that is the second statement that you give here. Now, normally we consider conditions for equilibrium when temperature and pressure are considered, and in order to get that, we normally have to consider the Gibbs function, because that is the expression, that is the function which has temperature and pressure as independent variables. So let's write dg, which is du plus p dv. Okay, so this is d of h minus ts. Let's d of h minus ts, which would be equal to dh minus tds minus s dt. And this dh can be expanded, which will be du plus p dv minus tds minus s dt. So now we know that TDS minus du minus PdV is greater than or equal to 0, which is basically equal to this is T delta sigma. Okay, so if I substitute this, then this will be minus T delta sigma. Sorry, this is dH is du plus PdV plus VdP, because this is u plus PV, so d of u plus PV is du plus PdV plus VdP. So what we get then is that this is T delta sigma. So if I take S dt and VdP to the other side, I'll get dg plus S dt minus VdP is equal to, this is minus T delta sigma. And since this T delta sigma is greater than 0, this is going to be less than or equal to 0. So at constant temperature and pressure, so if I maintain, so dg plus S dt minus VdP is less than or equal to 0 is the condition that you get from this one. So at constant temperature and pressure, therefore, the equilibrium is attained when the Gibbs function goes to a minimum. So at constant T, equilibrium is attained if G goes to G min. Right? So dg will go to 0 at G goes to D min. So that is the condition that you'll get. So you'll get a similar curve like this for G. So the G would go to a minimum in the case of constant pressure and temperature condition. So the condition for equilibrium at constant temperature and pressure for any system is that its Gibbs function goes to a minimum. So that is the condition that you would derive for system at constant temperature and pressure. So in the same way, we can actually also say for constant temperature and volume, we'll get a condition where the A is equal to 0 at constant T. So your condition for equilibrium will be the Helmholtz function goes to a minimum. Okay, so that is the condition for constant temperature and volume. Now, using this, now we will be using that at constant temperature and pressure, equilibrium is attained when G tends to G min, or dG is equal to 0 for equilibrium. dG at T 0 for equilibrium. So now using this, let us go to a multi-component system. So a multi-component system you'll get dG is nothing but V dP minus S dt plus summation of over I is equal to 1 to N of mu I dNi. Okay, so if I say dG at dP equal to 0 for equilibrium, this basically implies summation of I is equal to 1 to N of mu I dNi is equal to 0. So this is a condition for equilibrium for a multi-component system. So this is basically that. So now in a multi-component system, if each of these constituents is in different phases, so multiple phases are present. So let us say phases, let's say J is equal to, or alpha is equal to alpha is equal to 1 to P. P is the number of phases. Okay, so if each of these constituents each constituent I is present in P phases, I is alpha is equal to 1 to P, then this can be written in the form. So each of these phases then would be the mu I would mu I dNi okay, mu I dNi would actually be for each I, for each species I, mu I dNi will be the summation of mu I alpha dNi. So this will basically be a summation over the phases. So the mu I dNi for phase I would be equal to, so summation over alpha is equal to 1 to P of mu I alpha dNi alpha. So if I substitute this into this, then the condition for equilibrium or condition for phase equilibrium in a multi-component system is summation of mu I dNi is equal to 0. So summation from I is equal to 1 to N over the components of summation of alpha is equal to 1 to P over the phases of mu I alpha dNi alpha equal to 0. So now this is a very general and complex expression. And in this, we also know that when there is no chemical reaction happening, the number of moles of each of these species I is conserved when the constituent is when the composition is not changing. When the composition is not changing, then the summation of dNi alpha actually has to be equal to 0. When there is no because the if there is no chemical reaction happening, then the number of moles of any species when a system is completely closed would not be changing. So there is no spontaneous change that is happening. So the system is in equilibrium. Then the number of moles of I does not change, and therefore the phases can change from one to the other. The number of moles of species I in phase 1 and phase 2 can only change by one phase changing into another. So the summation of changes in each phase would actually add up to 0. So that is the thing here. Basically, Ni is equal to a constant, and therefore dni would be 0 over the phases. So this is basically what you will get. So with that constraint, you will be able to say from this is alpha is equal to 1, 2. So now this is a very complex thing to visualize. So let us take a simple pure substance. Therefore, there will be only n is equal to 1. So therefore, I is only 1 I is equal to only 1. So you don't need the symbol I anymore. Then let us say two phases in equilibrium. So let's take the example of water in liquid and vapor phases, and the phases are in equilibrium. Then alpha is equal to 1 or 2. That is the case that you would have. Then the equilibrium condition would be mu of species, the phase 1 and dn of phase 1 plus mu of phase 2. Phase is written in superscript. So mu of phase 2 and dn of phase 2 would be equal to 0. So this 2 that is written here is not square. It's actually the phase number 1 and phase number 2. So let us say phase number 1 is liquid and phase number 2 is vapor. Then you have mu 1 dn1 plus mu 2 dn2 is equal to 0 for equilibrium. Where did this come from? This came from this equation that we wrote here, that for each I, mu I dni, which is equal to the summation of these things. Okay. So now when there is only a single species, this mu 1 dn1 or mu dn is actually 0, and therefore this is equal to 0, which is the summation of this, which will be mu 1 dn1 plus mu 2 dn2. That is the expression that we have written here. So for a simple substance, this is this. And the conservation of number of moles will also mean that this, for this, there's I is only 1. So there will be summation over two species. So dn1 is equal to dn2. So that is the other one that you will have. So dn1 plus dn2 is equal to 0. So basically means that number of moles that go from the liquid phase to vapor phase plus the number of moles that go from the vapor phase to liquid phase is equal to 0. So because the n is constant, so dn1 plus dn2 is equal to 0. So in this one, then we can write dn1 is equal to negative of dn2, and we can substitute that into this one. So then I'll get mu1 minus mu2 into superscript into dn1 is equal to 0, or since dn1 in the general case when phase change is actually happening need not be 0, then for phase equilibrium, then mu1 is equal to mu2. So what have we found? For phase equilibrium in a pure substance with two constituents, the phase equilibrium will happen when the chemical potential of the same substance in phase 1 and phase 2 are equal. Okay, so the chemical potentials being equal in phase 1 and phase 2 mean that there is phase equilibrium existing. So what do you mean by phase equilibrium? There is no net change from one phase to the other. The two phases are coexisting, and the rate of conversion of phase 1 to phase 2 is equal to the rate of conversion of phase 2 to phase 1, and therefore their fractions in phase 1 and phase 2 remain unaltered under this condition. So that is the condition for phase equilibrium. So for example, if I have water at a certain value of dryness fraction, let us say x is equal to 0.5, then at that condition, if it has to stay at that condition, then the rate of evaporation is equal to the rate of condensation, and therefore there is no net change in X. Okay? So that's the condition for phase equilibrium. So when phase equilibrium happens, then the chemical potential of water in the liquid phase is the same as the chemical potential of water in the vapor phase. So this is the condition for a simple two-phase equilibrium for a simple substance, for a pure substance. Now, if I have multiple phases, let us say phase 1, 2, 3, let us say in water there can be three phases, solid, liquid, vapor. So if all three phases are in equilibrium, then we can show by the same arguments that for P phases of a pure substance, to be in equilibrium. So you understand, you visualize the condition for the triple point. The triple point is where the solid, liquid as well as vapor coexist in equilibrium. And when that happens, then you need to say mu alpha, okay, is same for all alpha. That is mu1 is equal to mu2 is equal to mu3 equal to mu alpha, mu p. Okay, so this is your condition for equilibrium of P phases in a pure substance. If I have to extend this to a multi-component system, that is for n components, each of which can be in P phases, then for each species, the chemical potential of all its phases will have to be equal in order that the phases are in equilibrium. So I'll say mu1 is equal to mu1 2 is equal to mu1 3 equal to mu1. Okay. Similarly, mu2 1 is equal to mu2 2 equal to so on mu2, and this we can write for all the n species. So I can write mu n 1 equal to mu n 2, etc. for mu n. Now this way there is equality, that is across phases of the same substance the chemical potentials are equal, but this way it is not the case. Okay, so don't make the mistake of saying mu11 is the same as mu21. mu11 is not the same as mu21, because this is not the condition for equilibrium. The condition for equilibrium is mu12, mu13, mu14. All the other phases of the same species would be having same chemical potentials, but different species can have different chemical potentials when they coexist in the mixture. Right? So the only condition there will be that when there is an addition or removal, in order for the system to be in equilibrium, the summation of ui, d, and I has to be 0 at constant temperature and pressure. So that's the condition that we will. Okay, so this is the case that we'll have. And as a special case of this, of course, we looked at for a pure substance in two phases, mu1 equal to mu2, which is actually G1 is equal to G2 in molar specific condition. Okay, so or dG, which is the change in phase, is equal to so if I differentiate dG1 equal to dG2. Okay, so this is your condition for equilibrium. Okay, so both of these would actually be equal to P dP minus S dt. Okay, because the number of moles of the species is not changing, it's a single component system. So this dG is actually dG1, which is the same as dG2, because these two are equal. The change in this is equal to the change in this, so this is the condition. So dg1 equal to dg2 is equal to v dp and s dt. So the v dp and s dt for the individual species would be actually equal. So v1, this should be the space, v1 dp minus s1 dt would be the same as v two dp minus s2 dt. So this is for a single pure substance, let's say liquid water and vapor water. So changing phase from phase 1 to phase 2, which is the liquid phase to vapor phase, or vapor phase to liquid phase. So this is the condition. So if I regroup this, I'll be able to write V1 minus V2 into dP is equal to, if I take this to the other side, it will be S1 minus S2 into dT. So at equilibrium, if I say dP by dt at equilibrium would be equal to S1 minus S2 divided by V1 minus V2. Now here, if I take 1 to be the vapor phase and 2 to be the liquid phase, then this actually would become Sg minus Sf, which will be Sfg divided by, so this is the molar terms. And we can actually convert it to the mass terms also, by divided by P bar. Okay, so this expression, so the dP by dt at the equilibrium condition would actually be, so this will be at saturation, would be actually equal to Sfg by Vfg. So this is nothing but your Clapeyron equation. Okay, so the Clapeyron equation basically tells you that dP by dt is equal to Sfg by Vfg. It simply comes from the equality of the chemical potentials of the vapor phase and the liquid phase when they are in equilibrium. So this is your equation. And the other thing that we need to understand from this constraint condition is what we call as the Gibbs phase rule. The Gibbs phase rule basically tells how many independent properties are required to specify the state of system in equilibrium like this. So actually, if I have n components, then n minus 1 states, n minus 1 variables are independent because the nth species, we can say the summation of mole fractions xi from I is equal to 1 to n is 1. So n minus 1 mole fractions can be independently specified. The nth one can come from 1 minus the summation of the others. So n minus 1 independent components are there. And in each one, if there are p phases, so n minus 1 into p will be the total number of independent variables if this whole thing is unconstrained. But since this is all constrained, for each species, okay, so for each of the n species, n multiplied by, there will be p minus 1 constraints because the summation of all the phases together would give me the number of moles of that particular species. So there will be a p minus 1 constraints which will be imposed here. This is equal to this and this is equal to this and this is equal to this. So there will be p minus 1 constraints. So n into p minus 1 constraints are actually imposed. So this will be f, which is the number of degrees of freedom of this system. That is the number of independent variables that need to be specified. So what would that be? Okay, and in addition, you have pressure and temperature. So there will be a plus 2 here. So what will that come? You'll have there is an NP minus P minus NP minus N plus 2. So this NP gets cancelled out, and sorry, this will be plus N. So this will actually be equal to N minus P plus, this P is the number of phases. So Gibbs phase rule basically says the number of independent variables required to specify the state of a multi-component multi-phase system is equal to the number of components minus the number of phases plus 2. That is the expression that you get. This is what you call as the Gibbs phase rule. So we'll take a pause at this point and start with the understanding of the calculation of properties of species in multi-component multi-phase systems in using the conditions of phase equilibrium for simplified cases of multi-component systems in the next class. So right now we have derived the condition for equilibrium from basic premise that an isolated system left to itself should go to a state of minimum internal energy when S and V are kept constant, or maximum entropy when U and V are kept constant. And we wanted the condition when T and P are kept constant, so we got that it should go to a condition of minimum Gibbs function when temperature and pressure are kept constant. So phase equilibrium is when multiple phases that are present in the same substance when the chemical reaction is not happening are present in equilibrium. And in order to do that, then when I equate the Gibbs functions, it gives me a condition that the chemical potential of each of those species in that multi-component multi-phase system should be equal for each species for chemical equilibrium, for phase equilibrium to exist for all the n species. So with that, we are able to get for a single component two-phase system the condition called the Clapeyron equation, and the number of independent variables required to specify for a multi-component multi-phase system is given by the Gibbs phase rule, which says F is equal to n minus P plus 2. So this is what we have done in today's class. We'll stop the lecture here and continue the topic